Hello, everyone who's joining us remotely. Welcome to this seminar, SMRI Seminar given by Uri Onn from ANU. You can take it away.
Thank you very much, Anthony. Thank you for the hospitality. Yes, the session. It's my pleasure. So I want to talk today about representation growth, in particular about the base change result in regards to growth of representation growth for arithmetic groups. So let me just set up the notation here. So suppose G is a group, and I will denote by R and G to be the number of n-dimensional, irreducible, complex representations of G, and of course up to equivalence. And throughout the assumption is that these numbers are finite, and even polynomial, as I will soon define. But there's going to be a variant to this definition, where instead of counting any irreducible representation, I will look at topological representations. So depending on the context, there will be variants. So these might be continuous representations, or there might be rational representations in case the group is algebraic. And let me already now put the definition that G has a polynomial representation growth if these numbers, there's a constant such that these numbers are bounded by a polynomial. And in such case, one can encode this whole series of numbers in a generating function, and that would be the representation zeta function. So the representation zeta function of G would be the Dirichlet generating function that one can cook up from these numbers. So another way to write it would be the sum of the dimensions minus S, where we go over all the irreducible representations of finite dimension. So typically we look at infinite groups, but this function is already interesting for finite groups. In fact, Frobenius already looked at this function, and so it has interesting special values. So the interest in this particular way of encoding these numbers, I mean, one can write down generating functions in various ways, but this particular one has three advantages. So the first thing is that when you write it as a Dirichlet series, this function is multiplicative. This is because the irreducibles of a product are just terms of products of the irreducibles. So another thing is that one can use complex analysis to look at the asymptotics of these numbers. So this zeta function, typically, if it has a polynomial representation growth, it will have some abscissae of convergence.
Sorry, Uri, there's a question in the chat about the previous thing. Masood is asking whether the two C's in that upper bound expression are meant to be the same.
Well, you can take the maximum. I'm not being precise about the constant here. It's just what's important here is there is a constant and there is a constant over there. So this function will converge in some like half plane. And the abscissa is exactly controls the growth of this sequence. So now the third point here in introducing this function is that it has interesting interpretations. So interpretation of special values, in particular, the value at even integers, they are related to counting homomorphisms from the pi1 of a Riemann surface of genus G into the group G. So the number of such homomorphisms, suppose that the group is finite, the number of such homomorphisms is the order of G to the power 2G minus 1 times the value of this zeta function at 2G.
Sorry, Uri, so you said that this is growth rate is exactly, it's not named super this and from one capital.
Yeah, so
I mean, when you say equivalent, do you mean named soup or limits of the ratio, blah, 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 blah?
So you're right. So the right thing to write here is that alpha G is the limit of the log of the sum over log of. Yeah, absolutely right. But just
Okay.
no, you're absolutely right.
Sorry, while I stopped, could you just draw a vertical line just to the right of where you wrote there and not right any further to the right? Yeah, thanks.
Okay, so if G is finite, then these numbers, they count homomorphisms from the surface group to G. It will be more precise here. So if you take the free group on 2G generators into and you count homomorphisms into a finite group, then this number will be G to the 2G. Just need to choose elements of G. But the surface group has one relation which you need to respect, and so the numbers that show up here, there will be G to the 2G minus 1. There will be a correction factor which is exactly this value. So that's where these functions show up. This is already a formula that Frobenius proved, but there are numerous variants of this phenomenon, of this interpretation. So if G is a complex semisimple group, then this you can interpret, you can evaluate the volume of certain modular spaces in TQFT using values of this function. And there are variants in various directions, which I will not discuss at all. What I do want to do today is to talk about the representation growth and representation zeta functions associated with arithmetic groups. So let me introduce the arithmetic groups that I'll be interested in. Other questions? Please drop me at any point. Okay, so the arithmetic group that I will be looking at, so as you know, the definition for arithmetic group can be quite involved if you make it precise. But for in this talk, an arithmetic group will be the following. So I will have a number field, and look at the ring of integers, and G would be semi-simple, simply connected algebraic group over K. And the arithmetic groups that we'll be looking at are G of O, just the integral points of G. At some point, I might take something slightly more general. I will invert some primes here, and then I will look at S integers. But basically, that's it. So G of O will be my arithmetic group. So, for example, you can think about SLDZ or say SLD of Gaussian integers or SLD of Z where P is inverted. So this is what I mean by inverting certain primes. So that's the freedom that we will allow ourselves. And I will be looking at the zeta function associated to these groups. And in what follows, if you're being irritated by general groups and you only want to think about SLDZ, that's enough. So the problems that occur, they are already very difficult for SLDZ and other groups. It's not the structure that is the problem. Okay, so the first thing I want to discuss is which arithmetic groups have polynomial representation growth. So it turns out there's a theorem by Lubotzky and Martin that says the following. Before that, I need to introduce a definition. So the definition is that G of O has the congruent subgroup property if for every finite index normal subgroup is G of O, there exists an idea in O, non-zero idea, such that N contains the kernel of that from G of O, G of O on Y. So that is to say, congruence kernels, they define the same topology as finite index normal subgroups, or finite quotients are dominated by congruence quotients. And for these groups, it turns out that these are exactly the groups that have polynomial representation group. So it's a theorem by Lubotzky and Martin. That G of O has the congruent subgroup property if and only if it has polynomial representation growth. So, for example, if you think about SLDZ, then it's a theorem of Bass, Mino, and Serre that it has a congruent subgroup property if and only if D is at least 3. So in particular, SL2Z doesn't have the congruent subgroup property, but it also doesn't have the polynomial representation growth property because SL2Z is almost free. So it has a subgroup of finite index which is free. And free groups, they have lots of representation. So these numbers are not even finite for SL2Z. Okay. And an evolution of this theorem. By the way, this is something I might talk about later on. So far, I've been dealing with characteristic 0 with number fields. This theorem, this direction, is true in positive characteristic, and conjecture in the converse is true as well. So in the same paper, Lubotzky and Martin proved this, I also proved this direction in positive characteristic. That is to say, instead of a number field, the function field of a field. Now, the next theorem, which really opened the subject, is a theorem by Larsen and Lubotzky, which says that if the group has the congruent subgroup property, which is going to be my standing assumption, this is the kind of entrance fee to the game. G of O has the congruent subgroup property, then the zeta function of O is a product of the zeta function of the complex points of the group times the product over all primes of the zeta function counting representations of G of OP that completion. Let me spell it out in an example. So that means that the zeta function for S and dz is a product of the zeta function of S and dc times the product over all the primes of the zeta function of S. Where the zeta functions here, they have different interpretations, and that has to do with my earlier remark here. So for these complex groups, we are going to count rational representations. And for these compact periodic groups, we're going to count continuous representations. And for these discrete groups here, we just count arbitrary representations. So here these are rational. And these are here, they are continuous. Now, what I want to do now is to give you just, I want to explain the ideas behind these theorems. I obviously can't describe the proof, but the ideas are very nice. So, the idea of the proof is the following. So, first, let's just construct representations naively. So, what we can do is we can take S and dz and we can embed it in S and dc. And this is a Zariski dense embedding. And so if we look at rational representation, irreducible rational representation, say for some GLMC, then since this is dense and this is a rational map, the pullback will still be irreducible. So we can just take whatever is known, then everything is known for the groups S and D C, for example, and pull it back to get representations of S and D Z. Now we can do this also for the periodics. So we can look at S and D Z P. Now this is continuous. And if we have, sorry, this is dense in the periodic topology. And now if we take rho to be a continuous irreducible, and this one is rational, into some GLMC, and we pull it back, it continues to be irreducible. So we can import and look at the continuous representations of this group and pull them back to S and dz. But you can do even better because S and dz embeds densely in products of these groups. For any finite number, if we embed it diagonally. So we can take products of representations, kind of outer products of representations, and put them back, and they still remain irreducible. Now, it turns out that in the presence of the congruence plus sample property, this is exactly what you need to say that you've done, that you got everything. So, in particular, what's making the trick here is algorithmic superutility. I'll say it without writing too much. The reason is that by algorithmic superutility, an irreducible representation of such group either agrees with rational representation coming from SLDC. So it's not that it is exactly coming from SLDC, but on a finite index subgroup, it agrees with such representation. Or it has a finite image. And if it has the finite image, and if you have the congruent subgroup property, it means that this finite image factored through the SLDZ. So either your representation rho in SLDZ is an extension. I write it like this because it's not really an extension, it's on a finite index subgroup, but that's okay. That's the finite index subgroup part is taken by the other primes. Extension to SLDC. Or it has finite image, but if it has finite image, then it factors through a finite quotient, but all of them, let's some n here, but the finite quotient are dominated by arithmetic quotients, but now you can pull the Chinese remainder theorem and get this one as a product over the primes. And so this is exactly how these come into life. Okay, so that was a sketch. Of course, some more things need to be said, but really the heavy hammer here is the Margulis autogeneity that takes care of the problem. So this is the reason that the congruent subgroup property is kind of entrance fee to the game. Otherwise, we are in a situation where there's no other methods that we can look at. And okay, any questions?
There is one for the representation zeta function as SLDC.
For SLDC?
Yeah.
So that's kind of exactly where I'm heading, but I'll say it now because that's what you asked. So in this business, this is the easy part of the story. So it's not that there's a closed formula, except for SL2 maybe, or it's the Riemann zeta function. But there's bi-dimensional formula, and so in principle everything is known. If you want, so for example, the abscissae of convergence of these local zeta functions is completely known. No, it's the rank of the group divided by the number of positive groups. But these factors, the local abscissa is greater, so they dominate, for example, the representation of the other part. But also, this is a very complicated business, which is the main thing that I want to talk about. How to deal with these local factors. So once we have the order point decomposition, whatever we want to set this function, we can attempt looking at these local factors. So, for example, the first natural question is what can be said about the abscissa of convergence of an arithmetic group? So, and the theorem is theorem by Nir Avni, which says that these numbers are rational. So, always under the congruent subgroup property assumption, Avni proved that the abscissa of convergence of O is rational. Now, in the paper where Larsen-Lubotzky proved this product formula, and they give many bounds and even precise values on certain abscissa, local abscissa. They put forward a conjecture, which is the next thing I want to talk about. So this is the conjecture by Larsen-Lubotzky. Which is the following. So suppose that gamma 1 and gamma 2 are irreducible lattices in a high rank semisimple then now I know you are very keen to know what is then happening, but let me first explain the terms before we say what they prove. What is this? What are all these things here? So a high rank semisimple Lie group so H is a high rank semisimple Lie group. It means that it's a product of finitely many groups which are simple over Fi a local field. So in this context, a Lie group would mean something like this. And why is it high rank? Well, it is high rank because the sum of the rank of Gi is at least 2. So that's what high means here. So, for example, SL2R is not good enough, but SL2R times SL2QP is already a good example. So this one gives 1, 1, and 1, 1, and learn business. Now, what do I mean about? So the second thing I want to explain is irreducible lattices. Yeah.
So they have to take like different local fields.
They don't need to be different. They could be the same. Yeah. So what do I mean by lattices or irreducible lattices? So it's a discrete subgroup of finite core volume. So Z in R is a good example. Z square root of 2 in R is not a good example, but you can fix it. So, so again, for the lattices or the irreducible lattices, Z in R is a good example. Z square root of 2 in R is not a good example, but you can fix it if you use the value embedding. So A plus B square root of 2 can now go to A plus B square root of 2 minus B square root of 2. And this is also an example of the irreducible lattice. What makes it irreducible is the fact that the projection of any factor is dense. So let me give you maybe another example. So another example would be Z 1 over P again in R. This is not a good example. You arbitrarily close to 0 here, but if you put it with QP, then if you're getting close to 0 here, you blow up here with that embedded. So here. So these are nice irreducible lattices, except that they are not lying in semisimple Lie group, but that can be fixed in a unit. So SLD Z 1 over P embeds in SLD R plus SLD QP. That's example from semisimple group in high rank with an irreducible lattice. And Jody, for your question, if you put SL2R plus SL2R, you can just use this one to get an example of irreducible lattice. Okay, so now we know what the terms are, and then I can say what they prove. So they prove that the abscissa of convergence of the two lattices is the same. So the two lattices can be completely different, but from far away, the representation well of these two lattices, of every two lattices in a Lie group, asymptotically the dimensions grow in the same way. Let me maybe make the connection to Searle's conjecture, but maybe I'll make it soon. I'll just remark that when we have the congruent subgroup property, we know that these numbers are finite because we have the theorem that says that polynomial representation is equivalent to congruent subgroup property. So these numbers being finite is exactly means that the group has polynomial representation both. And so the fact that they are finite is reflected by that. Any questions?
Kind of a bit different, right? Because before you had it over a global field, and now you're kind of
right. So I'm going to look at the representation both of the lattice. So these lattices and so it's going to these objects here. So they sit in hierarchy Lie group, but we are looking at them. We are comparing the representation of different lattices in the same Lie group.
and so there's not a priori product formula for these lattices. Like
No, actually, by definition, these are not product lattices. So by definition,
no, I mean like you have this like Euler product,
yeah,
of Larsen-Lubotzky,
yeah,
which was for a global field,
yeah.
and these guys in principle don't have such a product formula.
No, the object that I'm looking at is this is an arithmetic group, and this group has an Euler product. Now, yeah, what's confusing here is that I'm putting this arithmetic group inside a chosen two primes, the rings and one prime here. But now forget about this. Just think about it as an arithmetic group. It will have an Euler product decomposition over all primes. It's not this prime that or this prime that plays any particular role.
And then the problem is only for basically the other part, right? To get the same answer. Because for both of them, there is the complex part of this. It doesn't dominate actually. Say
Exactly. So exactly. No. So Sasha suggested to look at the local factors, which is what we're going to do. But the remark, as Sasha as you said, the fact that we know everything about all the abscissae conversions of the local factors still doesn't guarantee any knowledge about the global formula. So if you think about the Riemann zeta function, you do know the local factors and you do know the global one, but the local factors, they come in a very particular way. They are all 1 over 1 minus 2 masses. They look the same, and that's something which makes it easier to have a global local correspondence. So if you look at the local factors, you identify what's going on with them, you can deduce something for the global zeta function. But you can imagine that in this business, different things happen for different primes for the local zeta function. But the main issue here is that not too different. So that's where I'm heading. So there is connection between different primes, and this is why you can say anything. This is the underlying reason.
I'm just still confused. So in this particular example,
Yeah.
there's something z over 1 over qp.
Yeah.
So what would be the local factor for at p in the Euler product expansion? Would it just be SL dqp?
Oh, right. So in this case, you remove the QP part will not show up in the product. That's correct. So I try to say notation, and now I see that I should draw the S integers all along. So if you have primes that you inverted, they will not show up in the formula. Yes. Because you're right, there's no prime ID. P is not a prime ID here anymore. So it will not show up in the order product.
Here's a question.
Yeah.
This conjecture, when these two alpha values agree, does that mean that the polynomial growth is the same?
Sorry,
Does that mean that the polynomial growth is the same?
It means that the growth is the same.
Yeah.
But I can't say that the sequence is the same, of course. But asymptotically, yes, that's what it says. Okay. So the theorem, this is joined with Nir Avni and Benjamin Klopsch and Christopher Voll, is that assuming Searle's conjecture, the Larsen-Lubotzky conjecture holds. So what does Searle's conjecture say? It says that lattices in high rank semisimple Lie groups have a congruent subgroup property. So remember, these are the entrance field. We can't do anything without having this. So we can't beat Searle's conjecture in this sense. So simply because we don't have a method to construct irreducible representations of these arithmetic groups without the local considerations. But if you do know that you have a congruent subgroup property, then the Larsen-Lubotzky conjecture is true, and this the Searle's conjecture is known for in most cases. So let me make it even more precise. Searle's conjecture says that these two numbers are finite, because congruent subgroup property means polynomial representation growth. That means that abscissae is finite. The Larsen-Lubotzky conjecture says that not only that they are finite, they are equal. So that's the connection between them.
I'm a little bit confused, because if you have this property of being higher rank, you can have variable local fields. Yes, the Fi can vary. So what does the congruent subgroup problem mean in this case?
Well, it refers to
so you have to have a different I for each local field?
So the congruent subgroup property would refer to the lattice and not to the Lie group. So I'm here, but already here there's a question. So you can ask, what does it mean, the congruent subgroup property here? So the point is that by Margulies' arithmeticity theorem, lattices in high rank semisimple Lie groups, they are arithmetic. So they are of the form G of O, maybe localized by some primes. So once I said high rank semisimple Lie group and I wrote here lattices, this is just for short. We know that there's kind of a structure theorem for these lattices. They look like G of O's. There is an algebraic group, there's a ring of integers, and these gammas may be commensurable, and the abscissae is a commensurability invariant. So immediately it says that there is an arithmetic group. And
so give us an example of a lattice in SL2R cross SL2GP. So to sort of the greatest common divisor of groups or something like this.
But I think what's interesting about that is it actually cocompact, right? While right, this is even cocompact for many things, almost everything, right?
that I don't remember on top of my head.
Yeah, I think this one is one.
Yeah. Okay. Now I want to talk about. So I want to talk about this projection in the remaining
15 minutes.
time. But it turns out that because of the arithmeticity theorem that I just said, and because of some more structural properties, which of irreducible lattices, which I won't have time to explain, this conjecture will follow from another theorem, which says if the same again, that if we have L and K number fields and group defined over them over say the intersection, and we are and suppose that G of O L and G of OK, so the arithmetic groups coming from the ring of integers of them, suppose that they both have the congruent subgroup property, then the abscissae of convergence of the two are the same. So modulo some structure of just of the lattices kind of translation between the lattices to group of this particular form. This theorem implies this structure. Well, assuming Searle's conjecture exactly means that these two have the congruent subgroup property. So I want to talk about how we approach this this theorem. So now let's zoom into this group. So we call that we have the Euler product decomposition. And now this part is okay. We know everything using val. And in fact, as I mentioned, the abscissae of convergence of this part here is the rank of the group, say the root system, over the number of positive roots. This is by Larsen-Lubotzky. In the same paper, they prove that the abscissa of the other local factors is at least this number. So in terms of the global abscissa, we can throw this one out. Another theorem, the same set of authors, says that one can remove finitely many Euler factors without changing the abscissa. So really the focus is on these local factors, and even then on kind of the generic ones. So you can imagine that I'm starting with division algebra, the units in division algebra, say, globally. But then it remains in division algebra only in finitely many primes, and otherwise it will split. So generically, I will see a split form of the group. I will not see division algebras. So I don't need to worry about any finite number of bizarre groups or difficult groups. So really, the generic behavior is what matters. And so, how do we deal with these groups? So, what are they? So these groups are periodic analytic groups. So, what about the local factor? The normal community. So we have this G of OP. Think about SMDZP if you, and then it maps to the finite group of Lie type GF of QP. And the kernel is a prop P group. So this group is periodic analytic. One of the characterizations of a periodic analytic group is that it sits as a closed subgroup in some GLN-ZP. So that's what it is. And more than that, it means that every point is covered. So there's a covering by charts which look like ZP to the D. But these guys, they are even better. They are prop groups. So one source of representations of this group is coming from looking at these finite groups of Lie type, which, well, the linguistic everything is known. Well, not everything, but the dimensions are known. and the classification is known. So we can pull back representations and get representations of these groups. But most of the representations, they do not come from this kind of immediate suspect. They lie in the deeper, they go deeper and deeper in the group. And so there is a theorem by Harkin that says that if G is a periodic analytic with polynomial representation both, then the zeta function is rational. So there are integers and rational functions such that the zeta function is a sum of finitely many rational functions. Let me tell you a little bit about the proof of this theorem. So the idea is first to use the orbit method. So the orbit method in this context of propping groups says that the continuous irreducible representations of such a group, when I mean such a group, I mean this congruent subgroup, they are in bijection with co-joint orbits of G on the Pontryagin dual of the V algebra. So I can apply the log map and I'm getting a ring over the string of integers, local ring of integers. And there's a good correspondence between this group and the ring in terms of subgroups. And I can look at the Pontryagin dual of this ring as an additive. This is an abelian group. And the irreducible representation of G are in bijection with these orbits, where an orbit here would go to an irreducible representation, and the connection between the dimension and the orbit is that the dimension is the size of the orbit, is the square root of the size of the orbit. So these orbits are all finite, and that's the connection between the dimension and the size of the orbit. Wow.
Is it clear that this square number always?
Sorry?
An orbit?
Yeah, it's also it's a power of p and it's an even power of p. Oh. Yeah, so it has to do with symplectic. So there's a symplectic form there and also. Yeah. Okay, and so what one can do now is write down the zeta function as a, so it should be the sum of the over the irreducible representations of G1, and then the dimension minus S, but this is the same as going over the orbits and then taking them to the minus S over 2. But then you can write this down as a sum over all the characters and then kind of divide by the size of the orbit. And now you can massage this expression. You know, in calculus exams, sometimes you ask the students to prove that the sum is integral, and then it starts like that. At the end of the page, this sum symbol becomes an integral, but it is true, as in the Riemann case, in the Riemann sum, you can transform this expression into a periodic integral where you integrate over zp to the d. D is the dimension of the group. And then there is some function here which you can evaluate at p, and another function which you can evaluate in take p to the minus s, and write this down as an integral with respect to the power measure. Well, you can think about this just as the number of representations of a given dimension. So that's it's just a way to encode this sum in a very effective way. Now, if these were polynomials, then say smooth polynomials, then the number of points that this integral is clearly related to counting solutions modulo p to the n, and solutions modulo p to the n, they come in. You need to know what's happening modulo over fp, and then you have a geometric series because of Henz's lemma. Now, these are not polynomials; they turn out to be definable functions, but still, there's a theorem by the Nef that guarantees that this is a rational function. So this is the way Hiking proved his result here. Except that we really won't have time to say, but what we need, and Hiking's theorem is very general, it's true for any analytic group, and importantly, these functions, they depend on p. So there's no relation between, there's no other p's when you write down this theorem. But what we need in order to say something meaningful about different Euler factors, we need something which will help us to write it kind of schematically. We will have something like spec z in this direction and q bar in this direction. And so when we want to compare the Euler products, so let me just remind you what we are trying to do. We are trying to show that the abscissa of an Euler product over a field K is the same as the abscissa of an Euler product over a field L. So this is for the number field K and for number field L. And we want to relate those two zeta functions. We want to show that the abscissal convergence is stable under base change. So if we do, that's certainly true. So we want to compare these two type of zeta functions. So what we need to do is we need to somehow control primes on one side and primes on the other side, and we need to show that if something kind of is dominant here, the same contribution is dominant on the other side. So what we really need is to have some way to move in between number fields. So we need a theorem of this type, but which will be in a more restrictive situation because our groups come from a global object. That's the whole point here. The groups that we are dealing with, they come from the defined by number field. So this could be done. And using such a description, so it's a uniform description. So in fact, the zeta function, the local zeta function, is coming from a universal rational function which depends only on the group itself, the original group itself. And so there is a relation, there's that relation between these local factors. There is one point I should explain more, which is I talked about pro-P groups, and it's more difficult to handle these groups than these pro-P groups. So there's a Clifford theory involved here, which requires another complexity with definable functions. I will be really happy to talk with anybody who wants to, but I think I should stop now, and I'm here.
Are there any questions in the room?
Yeah.
So with this last thing where you go from K to L, so you're saying you did do that one prime at a time, or did you prove that as a global consequence of proving it one prime at a time, like you have a split, or did you, so how did you prove the abscissae convergence with the same? And did you do it like looking at a single prime and looking at the primes over it, or did you do it via some global thing?
There's a global formula which you could call it motivic. In a sense, it is motivic. There's a rational function which governs all primes in a motivic way, in the sense that you need to choose certain algebraic integers coming from the Veil conjectures when you specify to a given prime, but otherwise your function is uniform. But this is true only in the description of these groups. And so if we had a description in a similar way to these groups, then this conjecture would be much easier. I mean, it would basically reduce to showing you what the formula is and some kind of standard techniques. The fact that you need to go from such group to such group, but not in finitely many places, in infinitely many places. So finitely many places, they don't create any problem because this is a commutability invariant. The abscissae is an invariant for groups of finite index. But you need to do it infinitely many places. And so that really requires to do Clifford theory. And Clifford theory is not algebraic in this setup. At least we don't know how to make it algebraic. If we knew that again would be would solve the problem. That is to say, when we express the integral of these zeta functions in such a way, so we follow, in a way, follow Heikin's strategy, but we use the machinery and tools that we can rely on the fact that these groups are defined globally, then you can replace these definable functions by algebraic varieties. And this is the reason we can say a lot about the first congruence subgroup, but that fails when we want to go from here to here, and then brings back the definable sets and definable functions and complicates everything.
Yes. If you compare for a semisimple group G, the groups G of C and G of an algebraically closed characteristic P field, then presumably they have very similar properties with respect to this. Do they have the same abscissa of convergence, or is it P dependent at all?
I'm trying to answer the question. I think, if I understand so correctly, are you saying about comparison? We can say something like this versus something like.
No,
Kind of,
no, I'm comparing G of C, complex numbers, with G of FP bar.
But then it's not polynomial, right? It's not polynomial, right? In every domain, like you have.
The symbols are parameterized by nice weights.
Yeah, but you have a simple lambda, this is some dimension, but then all of its Frobenius twists are all non-isomorphic of the same dimension. So your R n will be infinite.
It's funny because if you look at it as the sum of dimension to the power minus s and make it a sum over the weight lattice, then the n which occurs for the characteristic P group is smaller than the other one. And yet what you say is undoubtedly true.
So
Yeah, is there anything known about there is a theorem of Avni which says rationals. Which rationals?
So two known cases.
What's the question?
So Avni says that abscissae is Russian. And Shasha says, okay, give me the numbers. So remember, if I want to write here SL2Z, I can't because Z is a free group, but I can still do SL2 if I really want, and I can just replace this by something not just make it. And so the abscissa in this case, the global abscissa is 2. Now, if you do this for SL3, then so this follows from Heike's in his paper. He just computes this for SL2. We computed SL3, which is a lot of work. It's 80 pages just to get. It's not just SL3. We need SU3. It's some more thing, but this becomes really, really difficult. You want to guess?
Yeah, I have one guess. Oh, yes.
So we put this, but Nir was quite disappointed because he thought maybe he put the wrong theorem, so maybe the value is integer. So it's clearly not going to be an integer later on, but we don't know. It's very difficult to compute in this business. So beyond these two values,
But do you know there are anything or something like that?
I don't know.
There can't be too many sequences that start 2-1.
And maybe one remark about these groups, by the way. In asymptotic group theory, like people study subgroup growth and normal subgroup growth in various zeta functions. And there's a big difference between these groups and these groups. So these might be polynomial growth, subgroup growth, and this one far from that. But in the cases that we do know to compute, it turns out that not only the abscissa is the same, the zeta function is the same. So not in too many examples. So this one needs to be SL2 or SL3 or SU3. The zeta functions, the number of representations of any given dimension is the same. Function three and number three. And it's a mystery whether it goes beyond why is the case.
Well, it seems like we've answered all the questions, so thank you.